We identify the non-constraints by identifying the constraints and then actively ignoring the non-constraints. So once we've identified that the 3 out of the 8 steps that might be causing a constraint, which are frame painting, power plane, and wheels, we have done our job of identifying the constraint, right? So frame painting, we said there's a constraint of changing paint colors. There's a constraint of custom colors. And we have to think about that because it's something that has a huge impact on the productivity of manufacturing. Also, the power plant, there's some cost of delay when we change power plant to power plant, cost of delay when we change over the wheels. In the second step, where we exploit the constraint, this is where we make the decision which is the most heinous constraint. Okay. Clearly, just based on our little anecdotal discussion about it, the most expensive and the most critical thing that we have to look at here is the frame painting, right? Changing paint colors is time consuming and expensive, especially custom colors, which is very profitable. So for all constraints in a system, determine which is the most impactful. We say in this system, it's the painting. And we have to follow the chains of impact and figure out how we can help work around this bottleneck. So here, we subordinate to the constraint. We delve into the root cause of delay and we figure out how to maximize throughput. Now, how could we, if we were, and I'll just guys, if you want to just pop up into the chat, if anybody wants to answer this question, what is a way that we could maximize throughput through the paint room? What's an obvious way we can maximize throughput through a paint room? Anybody want to guess? Okay, good one, Craig. But you're now spending money. Okay. You're right. Okay. We'll get to that in a minute, but good guess. John, I knew you'd get the answer. The way that we subordinate this is we make sure whenever we're painting any bike, I'll tell you why, David. It's up to you. In some cases, impact is more important. In some cases, ROI is more important. It's all about what you're attempting to do. I think in the world of the manufacturing metaphor, either one is fine. We're assuming that time to market and win-win situations are a good thing. But like John pointed out, bundling orders of similar paint color, that solves the problem. That maximizes our throughput. If we know that changing the color in the paint room is expensive and time consuming, then it behooves us to make sure we paint all the white bikes at the same time, and then we paint all the black bikes at the same time. So it changes the order of processing. Okay. We don't process each order as it comes in. We bundle the orders together and we figure out how to buffer the existing painting situation so that that never runs out. As soon as I finish my last black bike, I know ahead of time that I have to change that paint room. So I might have a drum buffer rope situation where when the 14th bike, the next to last black bike comes to the line, somebody gets a message that says, okay, after this bike comes through, there's going to be a cleaning. Sequence colors. Thank you, YouTube viewer. All right. And that's an example, once again, of the drum buffer rope. I keep pushing things through the line. I collect them up into a buffer. So I buffer all of my similar things together. I process them all together. You can do the same exact thing with software development. If you have your organization organized for throughput, you can do it. If your organization is not organized for throughput, then you need to get it reorganized so that you can do these kinds of changes and actually see the impact. And we do this drum buffer rope until we come up with a way of breaking the constraint. Now, like Craig pointed out, it's obvious if we let this go for any length of time, it may become obvious. And I may go and say, hey, maybe we need to shake it up a little bit and spend some money here. So maybe we elevate the constraint. This is now when we elevate the constraint, and now we spend some money. And I figured out that if we add another paint facility on the line, it will dramatically impact our overall speed to delivery. And the reason is I can always use both paint chambers and I can have two colors going at once, or I now have redundancy built into the system where if I don't have a heavy processing day, I can have one of my paint rooms be idle and be there for redundancy. If a paint room breaks down in this scenario, where do we go? We got nowhere to go. We got one paint room. But if we have two paint rooms, now I have that redundancy built in. And it basically means that I can increase my throughput. I have now broken this constraint. We spent some money. It was expensive. We put another $1.5 million paint room in there, but man, does it save time because we don't have to change paint as often. We don't hold up the line while we have to change paint. And we have the redundancy now built into the system where we didn't have it. This is all part of elevating the constraint. This is where we spend the money. What's the analogy in the software world? Hire some more testers, hire some more developers, hire some more product managers, hire some more product owners. That's how you break these constraints in the software development concept. Most of the time, most of the constraints that we face in developing software are people constraints, people-oriented constraints. Excuse me. Also, it's very important that we prove out our hypothesis of change. So I might be a senior vice president who pitches to the board of directors, hey, we got to spend a little dough here. And here's why it's worth the $1 million spend. Because if we make this spend, these are the benefits that it will give us. And we make a lean business hypothesis to purchase another painting room. And then we have to make sure that we measure before and we measure after to make sure that the throughput change is real. One thing we can't assess is whether the redundancy is helpful. But the first time your line breaks down, you are now producing zero value. So that in and of itself, it might be worth it just for the redundancy. My mantra is measure, change, measure, change, measure, change. We don't measure without the intent to change. We don't change without the intent to measure, because we can't tell whether our change is working unless we're measuring meaningful things about the change. And lastly, we now have broken the constraint of frame painting. It is no longer the worst constraint. Now we go, what's the next most impactful constraint? We may decide it's the power plant, and now we go after the power plant. We may decide it's the wheels. Here we decided it's the power plant. And the questions that we ask for the next most impactful constraint. What are the options? What will have the most impact? What will reduce the most waste? What will get our product out to our customers faster? And most importantly, what are workers and leaders going to embrace? Okay, we can't break constraints by making workers and leaders do unreasonable things. We have to have them on the side of change. And those are our real life applications of the theory of constraints.